Okay guys, welcome to your first video of Concepts of Physics in Rube Goldberg Machines. Today's learning intention and success criteria. So the first thing you have to be able to do is understand the role of, what you have to be able to do, is understand the role of different physics in a Rube Goldberg machine. So to be able to do that in the next two lessons, you should by the end of it be able to identify and describe a variety of physical mechanisms that can be used to cause chain reactions in Rube Goldberg machines. So in the last lesson, you had a look at different types of chain reactions and what they were and what a chain reaction is. Now today we're going to look at a bit more detail. What are some of the mechanisms or what's some of the physics involved in actually making those chain reactions happen? To do so, however, we really need to discuss Isaac Newton and his three laws of motion. In the late 1600s, this gentleman here, Isaac Newton, formalized three different laws which govern the theory of movement or motion. Now, the basic concepts that we'll discuss here formed his theory of different aerodynamics and the different forces that are applied in aerodynamics. So these were the basis for his aerodynamics work, which you've already looked at in first term. So Newton had three principles or three laws of motion, and these are it. Every object in a state of uniform motion will remain in that state unless an external force acts upon it. So something is going to keep moving. If something's moving in a uniform motion, so moving at a steady pace, it will remain that way unless an external force acts upon it. And I know probably some of you are already starting to think, oh, I know an example of that. Or I know an example of that in that last video. The second law, force equals mass times acceleration. So the force at which something, to work out the force of an object, it's mass times acceleration. I haven't highlighted that because it's very important, but we won't actually be doing these calculations in this unit. We will come back to them later on this year. And the third one, for every action, there is an equal and opposite reaction. Again, that's going to come into effect, and I'm sure some of you were seeing that go, yeah, that's interesting. I can see that example in our in one of those last videos that I watched from Rube Goldberg. A good way to think about the third law is that in every interaction there's a pair of forces acting on two different objects. So for every action there's an equal and opposite reaction. Easiest way to think about it is you sitting down on a chair. So there's two forces that happen as a result of this. There's called an action and a reaction. So you sit down, that's the action, and so your body gravitationally pushes down. Your body exerts a force, a downward force onto the chair, and the chair actually exerts an upward force onto your body. So for every action, there is an equal and opposite reaction. So I'm sure some of you are starting to think about those videos and can probably see a couple of examples of that. So with that in mind, we now are going to have a look. So now we've got the basic principles underway. We're going to have a look at a few examples of physics, the physics of mechanisms or mechanisms that you can use in your Rube Goldberg machine. The first concept that you need to understand is a lever. So a lever is actually a pretty powerful machine that can actually be used to move a large amount of weight or a large amount of mass or load with far less effort than it would normally take. It was discovered by a great mathematician, Archimedes, a very, very long time ago. And this is how a lever works. So a lever has a beam or a straight rod, as you see this red one here in the middle. And I'll just turn my pointer on, this red guy here in the middle. You also have this fulcrum or this fixed, hinge that sits here in the middle. You have the load on one end, which is the mass that you're trying to shift. And then you have the effort on the other side. The effort is the amount of required to actually move the object. So, I've got the fulcrum here, I've got a beam, I've got the load, and I have the effort. Now, the pure genius of a lever is the fact that utilizing this fulcrum or hinge here actually disperses the weight evenly along the beam. So the amount of effort or force it would take to normally move the load is minimized because the weight of the load is actually dispersed along the beam. So the best example of a fulcrum you might remember from your childhood is like a seesaw. So there's a fulcrum in the middle, there is one person on one end and another person on the other end. Now, if you've ever been the lighter person on a seesaw, you might notice that the other person goes all the way down and you move all the way up, yeah? But there is a way to counteract that, and that is to extend the amount of distance between you and the load or the weight that you're trying to lift. So you might remember as a kid leaning back really far on this beam to try and push the seesaw to make your partner go up and you go down. And some of the time leaning yourself out would actually work. And here's a short video to explain why.
4 times as far as you. Seesaws may be fun, but the implications and possible uses of levers get much more impressive than that. With a big enough lever, you can lift some pretty heavy things. A person weighing 150 pounds, or 68 kilograms, could use a lever just 3.7 meters long to balance a smart car, or a 10-meter lever to lift a 2.5-ton stone block, like the ones used to build the pyramids. If you wanted to lift the Eiffel Tower, your lever would have to be a bit longer, about 40.6 kilometers.
So what we're saying there is that you are able to actually lift a load by extending the beam towards the effort, or extending the beam out, dependent on the amount of load that you're trying to lift. The heavier the load, the longer this has to be, yet, a 56 kilo person is still able to lift all of those crazy amounts of weight, theoretically. The 3 different types of levers we have are the first class lever. That's the examples that we were just showing you there. That was with the fulcrum or the hinge in the middle, the effort on one side and the load on the other. So, the amount of force it's going to take to lift this is the effort, and the weight that I'm needing, or the mass that I'm needing to lift the load on the right. So a seesaw is a really good example of that. There's a range of different examples, but a seesaw, or, as Americans call them, teeter-totters, is probably the best example. Another type of lever is a second-class lever, where the fulcrum is at one end, or, the hinge is at one end, the effort is at the other, and the load is in the middle. The best example of a second-class lever that I can find you is a wheelbarrow. Now, in a wheelbarrow, I have the load in the middle, I have the effort, or, the wheel at the front that's taking all of the force, and the fulcrum is the hinge that, rotates, and that's the arms or the back of my wheelbarrow that, moves up and down. So that's an example of a second-class lever. A third-class lever has the fulcrum at one end, has the effort or the force applied in the middle, and has the weight at the end. The best example I can think of for a third-class lever would be something like chopsticks, where you're holding them in your hand and the hinge is at the end. The effort, or what you're trying to put at, the force that's being applied is all happening in the middle, with the load at the very, very end. Another really good example is nail clippers. Nail clippers with the load, or, what it is that you're trying to lift at the end, the effort happening around the middle, and the hinge at one particular end. And that's it, guys. They are the 3 different types of levers.